In this Mathematica Sessions video on discrete maths, we'll be looking at the Euclidean algorithm and further topics such as proving things by mathematical induction. If you're interested in that, you should stay tuned. And so this week we'll start by looking at some GCD calculations using the Euclidean algorithm. Okay, so we're going to calculate first the GCD of 221 to 255 because I can just maybe it's best to leave some of these for you to do on your own. All right, and if you want to do this with me at the same time, please feel free, right? If you've got some paper and pen handy for doing these yourself, I suggest that you go ahead and do that. Okay, so how do we do this? So the first thing we want to do is take the bigger number, and in this case, if we're doing C, then it's 255. So we're calculating this GCD using the Euclidean algorithm. So we put 255 equals, and then what I do is I'll leave a space, try to denote that with an underscore, something times the other number, 221, and then plus something else, right? So that's what I do just as a reminder for what I'm actually calculating. So what you want to do is calculate the quotient and the remainder for 255 and 221. All right, so I'll put this part of it in a comment, and then let's just go ahead and calculate. All right, now if you're doing this by hand, you would be taking 255, and I'll just put a 0.0 so I can do a division, divided by 221. Okay, let's find out what this is. So here we see 1.15 and so on, right? So that tells us that the quotient here is the number 1. So in other words, the floor of this, right? And I can do the same thing with this built-in floor function, right? Which I don't know if you have that on your calculator, but it just takes the greatest integer less than or equal to the number. Okay, anyway, so this is the number 1, and we just place it right there. Right, next we need the remainder. So now that's easy because all we have to do is do some algebra on this, and that's 255 minus 1 times 221, and this is our remainder. Okay, so this now we see is 34, and so we can just fill this in. And I'll leave some space so it's easy to look at. Any questions on that? That's pretty basic. That's just using the quotient remainder theorem on two numbers. All right, so moving on. Next, what we want to do is pull down some of these numbers. Now, what we do is we pull down this 221, and now we put that over on the left-hand side, 221. Okay, equals, and then we have our something times 34 plus something else. Okay, and so we've got to find these two numbers. So what's the quotient? What's the remainder? So I can repeat these calculations again, just here. Of course, you can do this by hand or with a calculator. So what we want is the floor of 221 divided by 34. Okay, so we get 6, and we put that quotient there. And then we calculate the remainder in the same way. So 221 minus 6 by 34. Okay, so 17, and we put a remainder there. And then we repeat this. We're nearly done. So what we do now is we take this 34, that was a previous remainder. We put that on the right-hand side. And we have equals, and then something times 17 plus something else. All right, now, if you know your times tables, well, then you'd know that 17 times 2 is 34, right? So we know straight away that this number is 2, and this number has to be 0, okay? And when you get 0, you know that you're done with the Euclidean algorithm. Now you just have to interpret the result. So here the greatest common divisor of 221 and 255 is this number right here, 17. It's the last remainder above the 0, so this one. Okay, so I'll just write that here. This is equal to 17. Okay, and that completes that calculation, which was fairly easy. Okay, how are we going? Any questions on this? You can give me a thumbs up or a thumbs down, or put something in the chat. Let's see whether I can open up the chat in here. I think I can. That'll be handy. For some strange reason, that seems to work well when I'm at UQ, but it doesn't work well on my own computer here. All right, so I'll have to stop the share and open up the chat if I see that someone said something. Okay, but anyways, you can turn off your mic and just interrupt and say something anytime too. So feel free, don't be shy. All right, just gonna have a look here. Okay, great. So let's move on then and have a look at another question. Oh, incidentally, in this software, I can simply calculate the GCD within it as well. So GCD 255, 221, press the button, and you see I get 17 here, which is handy. Okay, let's move on. Have a look at the next question, which is 5.1. So it says, write the sum of these things in summation notation. Okay, so to do that, I'm going to need to borrow some summation notation from another question because I've already used the palette to pull that up. And so I'll just write that here. So we'll go from, just put something in bracket as a placeholder. Now, what we want to do here is look for a pattern in these terms, all right? So the brackets are there to tell us to think of these as separate items to put as summands in our sum. Okay, so can you see a pattern here? Now, if you look at the coefficients, we have a coefficient of 1, we have a coefficient of 2, 3, 4, and that should have been a 5 there. That's my mistake. Okay, so the coefficients, we want those to be j, all right, and then we have x to the power of something minus 1. But these powers have a pattern also. So they start with 2, 3, 4, 5, and 6. Okay, so it's 1 higher than the coefficient. So let's put j plus 1. And then where does this stop? Well, it would stop with j is 5, right? So we put a 5 up at the top here. Okay, now I can just test this out and see just by pressing the button here, because Mathematica allows you to do exactly that in the syntax. All right, but what it gives us is not quite what we had up here. So at the same time, I could just evaluate this below it and see if these are the same. Okay, yes, those look like the same thing, so I'm confident that that's okay. All right. And of course, you could do this by hand too, but it just, takes a little bit of time. Okay, great. Let's move on and do this one. Evaluate the product. All right, so I'll do this by hand. So this product, just like a sum, except we're multiplying. So we put in I is equal to 1 as our first multiplicand. So 1, and then this is times 1. All right, now the next one is multiply this times the same thing, but when I is equal to 2. Okay, so we put a 2 there and a 2 here. And we do the next one, which is to put in a 3 right here. Okay, and then we do it again until we get to 5. So put in a 4, and then put in the 5. And of course, you could just punch it into the calculator right here, but you want to do this by hand, I think. Okay, so we need another line now. So we can use the commutative property of multiplication and just put all of the single numbers together, right? We can see we have 1 times 2 times 3 times 4 times 5. So let's pull all of those out and put them right here. So 1 times 2 times 3 times 4 times 5. Okay, good. Next, what we want to do is evaluate each of these powers of -1. Some are odd powers, some are even powers. So the odd powers give -1. Okay, so just do that. That one's -1. -1 squared is 1. So we can just eliminate that because it's just 1. And then -1 to the power of 3 is -1. -1 to the power of 4 is 1. So I can eliminate that. And then we have -1 to the power of 5, which is -1. Okay, now here we have 3 of these -1s. So that comes out to -1. And so that's -1 times 5 factorial, which is it 120? I think so. So just put -120 here. Okay, great. I assume there are no questions, so let's keep going. All right, so the next one, write this product in product notation. So again, we're looking for a pattern, just as we did with the sum that was above. We looked for a pattern and then we wrote that in summation notation. So let's borrow this summation notation, copy and paste this down here. Of course, you're writing that by hand. Okay, so I need a, write in product notation. Okay, so I need a product, not a sum. And so we have y to the power of something in it, all right? So I'll just grab one of these and I'll put it here. And we can get rid of these other letters. Okay, so it's not quite correct yet, right? Now we look for the pattern. So we have y to the power of 1, y to the power of 2, up to y to the power of 4, and then we're subtracting the same number. So then we could put a j there and a j here, and a j down here is the dummy variable, and now we're summing from 1 to 4, so we would stop at 4 there. And I can even evaluate this, so I'll just do it, and we can see that this is the result, and it agrees with this one right up here. Okay, great. Question 5.1, D. Evaluate this sum when n is equal to 5. Okay, sure. I'll copy and paste that here. And we'll just enumerate some of the terms. So we're subbing in n is 5. Okay, and so that means we add up 5 of these, subbing in the appropriate j values. Starting with 1. And then this one is 1. Okay, but we have 5 of these, so I'll just copy and paste this 5 or 4 more times. And then I'll change the numbers. So the second one was subbing in 2. And then the third one subbing in 3. Then we sub in 4. And then we sub in 5. Okay, and then all you have to do is simplify this. So let's make another line and simplify that. So this is -1. And then we can just see this as 1/2. Now, -1 squared is 1. So now we have 1/4, 1/4. Okay, -1 cubed, that's -1. And then 2 to the power of 3 is 8. Okay, minus 1 to the power of 4 is 1, so we can remove that. And now we have 1 over 16 there. And then we subtract, because that's minus 1 to the power of 5, which is minus 1. So we subtract 2 to the 5th, 1 over 2 to the 5th, so that's 1 over 32. And then we just add these up. Okay, so of course you want to get common denominators, but this is fairly easy. So I can probably just do this with a computer, assuming that that's okay for you to do yourself. Of course, most of these are okay for you to do yourself because they're easy. And we get minus 11 on 32. If I've spaced that out properly, I think it's okay. Yep, good. Okay, great. Let's move on. Now we've got some proofs by induction coming up. So several, in fact, all the rest of these are proof by induction. Okay, so the basic technique is to do so for the first one, form an induction hypothesis, and then use the induction hypothesis and show that it holds true for the next one. Okay, so we'll do that here. Now, this first one is really obvious, right? So it just says, prove that for all positive integers, n times n plus 1 is even. But we can see that if n is even, then we're done. If n is odd, then n plus 1 is even. So this product is even, right? So there's a proof of it. But that's not a proof by induction. So that's what we need to do here, form a proof by induction. It gives a really basic example of how to do this, though. So now, let P of n be the statement. P of k, we'll go P of k. So we'll say let P of k denote that statement holds for k. Okay, and that's a handy thing to set out because it allows you to save some space in writing. All right, so this is a proposition that could be true or false. Okay, so what we want to do first is show that P of 1 holds true. Okay, so what we do is we just take this and we put in 1. So 1 times 1 plus 1 is 1 times 2, which is 2, which is even. So P of 1 holds. Okay, good. Now we need to form our induction hypothesis. So we'll say, assume PK. Then we could put a full stop, right? But what we're assuming here is that the statement holds true for when n is equal to k. So we'll reiterate this here. We assume that this is even, and now we'll change the n's to a k, for some positive integer k. Okay, so this is the induction hypothesis. So I'll just put I.H, abbreviating induction hypothesis. So it's important to set that out. Okay, then what we do next, now that we've got that, now this one's a little bit tricky because you kind of want to see where you're going. So on a piece of scratch paper, you can put in what would be the next term, right? Okay, and so what I do here is I take this and I just replace the k's with k plus 1s. We have k plus 1, but that's k plus 2, so I'll just write it like this. Okay, so we want to look at this, but we want to use the induction hypothesis at some point, which is right here. So, so we might say, just start an opening line, something like now. this is equal to, and then we ask ourselves, actually, how do we use this induction hypothesis? How do I recognize this k times k plus 1 within this? Okay, so if you just expanded one part of it, you would have, in brackets, k plus 1 times k plus 1 times 2. And now that gives us an opportunity to use the induction hypothesis. Okay, so let's use it now. So this is equal to 2 times a plus 2 times k plus 1 for some positive integer a. And this is true by the induction hypothesis. So let's just say that, by induction hypothesis. Okay, and then now, so following from that assumption, we can just factorize this, pulling the 2 out. And so we see straight away that this is even. Okay, in other words, if the induction hypothesis holds true, then it holds true for the next one, which is k plus 1. And so at this point, I'm going to reiterate what we've done. But I should say, comma, which is even. Okay, and now I'm going to reiterate that now. So we have shown that if p of k, comma, then p of k plus 1. Okay, so it's like you have a domino and it knocks over the next domino, and that next domino knocks over the next one after that, and so on, until you knock down the infinitely many dominoes in the chain of integers. So that's why this works, right? So, but you need to connect the dots by citing the principle of induction, which is a theorem. Okay, so then you say by the principle of mathematical induction, the result holds true for all positive integers. Okay, but you can always abbreviate principle of mathematical induction by PMI, okay, because we understand what you mean when you say that in this course. Any questions? All right, everybody's silent, so I guess that means no questions. Thanks, Jinyu. So let's continue on with the next one. Okay, another induction question. So I'll scroll up to the top now. I think I'll leave a bit more space so we don't have too much to confuse us. So the next one says, prove by induction that for every, well, it's integer, but for every integer greater or equal to 2, n cubed minus n is a multiple of 6. And another way to phrase that is 6 divides n cubed minus n. Okay, so what we want to do here is, now I'll copy paste here because I can do that with a computer, right? So I'll copy paste this. Okay, but you don't, you probably don't need to do that because it's pretty clear what you mean by P of K after you do 1 or 2. Okay, so then we want to set out the first one. So the first one in this case looks at when n is equal to 2. Okay, so we put 2 to the power of 3 minus 2, and then we can just evaluate that. So that's 8 minus 2, which is 6. And so we say, which is divisible by 6, isn't it? Okay, and so P of 2 holds true. Okay, now that we've done that, we need to set out our induction hypothesis. Okay, so copy and paste some of this. Induction hypothesis. So at this point, we assume that this is a multiple of 6, where we replace the n with a k. All right, so given that, we want to think about where we're going with this. So on a scratch paper, you can do some calculations, right? But I'm going to frame this in a way that's similar to what we did in the last one for showing that that number was even. N times n plus 1 was even. So let's get out k plus 1 cubed, and then minus, in brackets, k plus 1, because this is the next one we're interested in, which would be the statement for p of k plus 1. And then we'll just open this with now this is equal to, okay? So what we want to do now is expand this. This is easy to expand in your head because using, say, Pascal's triangle, you have that the first term there expanded is k cubed plus 3k squared plus 3k plus 1, and then we are subtracting k and we are subtracting 1. Okay, and now we want to simplify this. So let's just simplify all of that. So copy and paste. All right, so what can we cancel here? So we've got a 3k there and a minus k, so this will become a 2k, and we can eliminate that one, and then 1 minus 1 is 0, so we can get rid of this. All right, great, but now we have to relate this to k cubed minus k in order to use the induction hypothesis. So can we realize this within this? Yes, we can. In fact, we can just take that and put it there, provided we compensate for it. Okay, so right in here, I will put in a minus k, and I'll put in a bracket around this, but at the same time, I have to add that k so that they vanish, and so that these two lines are actually equal. Okay, but you can see that I could just add the 2k and the k and make this a 3k right here, right? So let's do that. All right, so now that I've got that, now I can use the induction hypothesis. And so copy and paste and use the induction hypothesis, and that would say that this one that I've got in brackets here is divisible by 6. So I'll say that's 6a, where a is a, say, an integer. Okay, good. And then while we're at it, we can just factorize the right-hand side of this, okay, because you can see straight away that they both have a common 3. So we'll pull out that common 3. And you can also see that there's a common factor of k there. So let's pull out the common factor of k, and that would leave a k plus 1. All right, and now we can just use the fact that k times k plus 1 is even. We've already proved this, right? But let's just say that we're using the induction hypothesis. So we'll say by induction hypothesis. Okay, good. And so next we'll just say this is 6 times b, where b is an integer by what we've done above, basically. So I'll just say by above to abbreviate that. And we can see that this is divisible by 6. So let's just note that divisible by 6. Okay, so now we'll reiterate what we've done, but I'll just copy and paste that. And actually, I can just copy and paste all of this because it's the same statement. Okay, so we have shown that if pk, then pk plus 1. And then you've got to write this. There are usually some some marks awarded for writing this, or some subtracted if you don't put this, right? That is the last line. You need to put by PMI. It's important because it's not true without relying on that theorem that the principle of mathematical induction holds. Okay, any questions?
I got a question.
Yeah, go for it.
If this question is isolated, it means do we need to prove that k times k plus 1 is even, or we just say by integer, by.
Okay, so your question is basically, if this were a standalone question, like an exam question or an assignment question, would you need to prove that this part k times k plus 1 is even? Is that what you're asking, Jinyu?
Yes. Do we need to prove that?
I would say no, because it's really obvious, right? I would just say it. So I would just say this is, at this point, I would say, I would just, as we have it here, and then let's just actually write this.
All right.
So let's just say since this is even. And I would say that you can do that just because it's so completely obvious, right? That that's even.
Yeah, sure.
Wouldn't you agree? So if it were an exam question, I would think that that would be okay, unless the exam question asks you to explicitly prove that k times k plus 1 were even, right?
Yeah.
And that could be the case, right? Because sometimes you need to give some easy marks on exams too. Okay, any other questions?
I'm cool. Thank you.
All good? It's a very nice day outside. Incidentally, in Brisbane, don't know where you guys are, but it's a nice day in Brisbane. Springtime seems to have started. Okay, so another induction question. Prove by induction that for every integer n greater or equal to 2, the square root of n is less than the sum of 1 over the square root of k. Okay, so this is how it's how it is written in your tutorial problem, right? And so I left it that way, excuse me, but I'm going to change the problem right now in front of you because we can, right? So just because a lot of us are in the habit of using k as the induction letter, okay, so you can, if you like, just change this to a j so that the statement is written in terms of j. And now I've not changed anything here in the statement. It's the same statement, right? Because that j is just a dummy variable, so we can use anything. We could use Jason if we wanted to, or J for Jason. Okay, so let's prove this by induction. So what we need to do is we'd set out the usual stuff. So I'll copy and paste from the last one. All right, so there we go, and make that a comment so that I don't accidentally execute that and get an error message. Okay, so we've got our notation now. So what we want to do first then is evaluate this for the first one. So on the right-hand side, what we have is this sum up to 2, because that would be the first one, right? 2. Now let's just evaluate the sum. So we have 1 over square root of 1, and then 1 over the square root of 2. Okay, so you want to compare that with the square root of 2, which would be on the other side. Okay, so let me take this and put it on the left-hand side here. Okay, so these two are equal. Now I want to simplify what's on the left-hand side. And so what we have, so the first term is just 1, right? But the second term, we can write that as root 2 over 2. And this is just 1 over 1, right? But I can put that 1 over 1 as 2 over 2. and combine these so that what we have here is 2 plus root 2 over root 2. Okay, do you guys follow that? Yes, no? Just some basic arithmetic there. Now what we want to do is compare this with root 2. Okay, so I'm just going to say that this is greater than root 2. Now, if you want to actually verify that, and you should, you've got a couple of choices, right? You can just punch it into the calculator, see that it's true, but that's a little dodgy, let's say. Just punch it in the calculator and see that it's true. Instead, what you want to do, probably, because it's a little more elegant, and you can be wrong in your truncation errors just by punching it in the calculator if they happen to be close. So what we want to do here is work backwards with this right now. So we would say multiply throughout by 2, and then we'd get this. Okay, but next, if we do some more, let's see, I would subtract this root 2 from both sides. Okay, and so I would have one of these root 2's less than 2, right? Okay, and so this would be your starting point. So now that we've worked backwards, right, this is an if and only if statement, but we want to say it the other way around. So I'll copy that, and I'll say that left-hand side is true since root 2 is less than 2, and that's the same, incidentally, as saying 2 is less than 4. So we have the next line, this one, hence we have this inequality, okay? So the conclusion of that then is that the statement holds for n equal to 2. So we can say P of 2. Okay, any questions? Rightio. Okay, so the next one is we need to set out our induction hypothesis. So we go IH, induction hypothesis, which is P of K, but let's write it out. And now you can see why we changed the letter K to a J earlier. So we're assuming then that this holds for n is equal to K. And now you want to be careful because you're summing over J, right? And so you're just taking this and replacing the n's by K. So we need to write out assume PK, which is this statement here. All right, now what we want to do is play around with this. See, how can we get the statement P of K plus 1 legitimately from this by applying legitimate operations, or arithmetic. So we want to have a K plus 1 in up top here, right, in the statement for P of K plus 1. So it might help you to write on scratch paper what the statement P of K plus 1 is. All right, but what we'll do, because we want to follow the logic in the correct direction, take the induction hypothesis and show that it implies the statement for P of K plus 1. Okay, so I'm going to say on both sides we're going to add, so adding. Now what would happen if we put in K plus 1 at the end? We would have 1 over the square root of K plus 1. So that's what we want to add to both sides. So adding 1 over the square root of K plus 1 to both sides of the inequality, what we'll have then is, let's see, so I'll put this in front, so that plus that, and then on this side I'll put it on the right hand side. Okay, so we've just done that, and now that we've done this, remember why we did it. It's because this becomes part of the sum, right? So I'll put in brackets, give some space, this is equal to, that's not a smiley face, I just mean to say this is equal to, on the right hand side, what happens when I put k plus 1 at the top, right? So you understand that? Just let us know if you need that clarified, but I think it's okay. All right, so this is what we have now on the right-hand side. So we need to simplify the left-hand side because we need to show that this is greater than the square root of k plus 1, because that's what we would have here if we replace the ends by k plus 1. Okay, and this takes a similar sort of analysis to what we did up here. All right, so let's play around and work backwards. So I think it's going to be true, so I'll just put this, and then I'll just say why that happens, okay? I'll say why that happens below. But I'll work backwards with this to come to it, and then we'll change things. Okay, so what we want to do is take this and simplify it. So we can multiply by root k plus 1 on top and bottom, and we get k plus 1 there. All right, good. And now we want to combine these fractions. So I would basically multiply this by k plus 1 and then put it over k plus 1. So that would amount to, without me creating another fraction, putting that up in the numerator with a k plus 1. Okay, so we'll have this plus. All right, so these two right-hand sides are now the same. All right, and now I want to, let's see, what do I want to do? Multiply both sides by k plus 1. Now I'm doing this with keeping in mind that I want to be able to go backwards with this. So, and it follows that I can go backwards with all of the steps that I'm making. In other words, if this line is true, then this line is true, and then this line is true, and so on. Okay? So that's what I'm thinking about now. All right, next, let's see, have a look at the like term. So this is a like term with this one. So we'll subtract the square root of k plus 1 from both sides. And so that would have the effect here of just taking one of these out of this. And so we would have just a k times the square root of k plus 1. All right, now this holds true because it holds true for their squares. So in other words, if I square this, then what I have is k plus 1 here, and I have this k being squared, and then likewise k plus 1 squared there, and then a k here. All right, now, yeah, so you could expand that and show that it's in fact greater. So let's do that. Let's expand both sides. All right, so on the left we have k cubed plus k. And on the right we have k cubed plus 2k, k cubed plus 2k squared plus k. And then you can see that what we want to start with and go that way is, so we'll let the k cubes vanish here. Let's get rid of those. And then, seems like I might have done some dodgy arithmetic here, have I? Yeah, I have. So that should have been a k squared right there. Okay, so that changes things a little bit. So we got this. So this is a k squared now. Okay, and then the last line is that subtracting k squared from both sides, this is positive, and you can see that that's true when k is the positive integer. So now all you have to do is take all of this backwards, and since I'm on a computer, I can easily do that. So I'll go start with that line, then go to this line, then go to this line. Okay, Then we'll go dot, dot, dot. Finally, we get this. All right, and then I can just get rid of all of this because that was scratch paper working. And then I'll say since. So yeah, that's the way we want to do that, right? Now, the number of details you put in on that, it's probably up to you. Okay, and then now the last thing we have to do is just fill in the rest of the stuff. So say what you've done and then write the principle of induction, because this is the statement here for k plus 1. So we have in fact shown that pk implies pk plus 1. And the induction is now complete because we've done that. We just needed to write this. All right, any questions on that? Anyone? No? Okay, great. So let's move on and have a look at the next one. Now this one I think I'll just leave to you to do yourself. It's fairly straightforward. Let's have a look at maybe the last couple. All right, 5.3 and 5.4. So 5.3, we've got a sequence. It's recursively defined, but it only takes in the last one. So this is telling us that we only need ordinary induction to do this. So I'm going to change this to a j again. Okay, so for j greater or equal to 2. Okay, and so we do this for the first one. So in other words, a2 is equal to a1 divided by 2. And then what was a1? It's 2. So this is 2 over 2, which is 1. And then the statement says, prove that that's 2 over, in this case, 2 over 2 factorial. So this is 2 over 2 factorial. Oops, wrong symbol. And 2 factorial is just 2, so this is right. Okay, good. So we got the first one. So this is P of 2 holds. And I'll turn this into a comment as well. Okay, good. So continuing on, now we need to make the induction hypothesis. So that would just be to assume that a subscript k is equal to 2 divided by k factorial. Okay, good. Now, how do we use the induction hypothesis? Now, remember, we're allowed to use this part. So you can say we have this holding, but now we want to change this in terms of k plus 1. Okay, so that would be, this would be k, and then this denominator here would be k plus 1. All right, so this is just the definition that we're writing here. So we have this. Next, what we want to do is use the induction hypothesis. So let's say by definition. And next, we want to use the hypothesis. So we'll rewrite this, except here for ak, we're putting 2 over k factorial. Okay, and now this is by induction hypothesis. And now all we have to do is simplify this. So this is equal to, and we take this, right, because this is 2 over k factorial divided by another k plus 1, and that becomes the same as having the k plus 1 in the denominator. Okay, good. I can get rid of superfluous brackets. Next, we just realize that this denominator is k plus 1 factorial, and we're done. So this is 2 over k plus 1 factorial. And so we have shown that p of k implies p of k plus 1, so I can just basically copy and paste the ending. All right, great. Now the last one is about Lucas sequences, but the difference here is that, like the Fibonacci numbers, this takes in the previous two terms. So now we need a strong induction hypothesis and a strong induction theorem. So, okay, so we've got to prove that the terms are less than 7 over 4 to the power of n for all n. All right, so we'll notice that the number 1 and the number 3 are less than or equal to, let's see, so we put 7 over 4 to the power of 1. And then the other one is 7 over 4 squared, which is equal to 49 over 16, right? So yeah, that's true. So 49 over 16 is greater or equal to 3 because 3 times 16 is 48. Okay, so we see that we have P of 1 and P of 2, which are the statement for the first two terms. Great, so let's make this a comment. Put some space in here, and we'll continue. Okay, so we need a strong induction hypothesis. So I'll put SIH for strong induction hypothesis. And that would be assume that this holds true, where we replace the n by a k. But let's say for all k less than or equal to n. Okay, so this is a stronger statement than just an ordinary induction hypothesis. It's a strong statement because we assume that this is true for all k less than or equal to n. Okay, so now let's use the definition. All right, so by definition, we have this, right? And I should have changed that to a j, so let's go ahead and do that. Okay, so the definition now, I want to use a k because I'm going to rely on the induction hypothesis at this point. So this is less than or equal to, and what we have here, because this one is less than or equal to 7/4 to the power of k minus 1, so put that up here, and then the next one, 7 over 4 to the power of k minus 2. All right, good. Okay, now we've got to show that this is less than 7 over 4 to the power of k. And now all we have to do is do some factorization. So we can factor this one out of both terms of this sum. Okay, so I'll just put it here again. But I'm going to factor this one. Actually, you know what? I want to factor out 7 over 4 to the power of k. That'll be easier. So okay, so I'll copy this, put it out the front, and then get rid of that minus 2. So what I'll have now, 7 over 4 to the power of minus 2 there, because we've taken out 7 over 4 to the power of k, and I'll get rid of the k in the exponent there as well. Okay, so now we have 7 over 4 to the power of k here, because that's the inequality we're aiming for, right? All we have to do now is just simplify this. So let's just work out what this is using the computer, but you can do it by hand. Okay, so we have 44 over 49. Okay, so I'll copy that and paste it. So this is equal to 7/4 to the power of k multiplied by 44 over 49, but 44 over 49 is less than 1. So this is in fact less than 7/4 to the power of k. All right, and if you look at what's over here and what's over here, what we've done is we've proved that this holds for P of k. So let's reiterate here what we've done. We have shown that P of k minus 2 and P of k minus 1 imply that P of k, basically, right? So in other words, if we assume that it holds true for all k less than or equal to n, then we can show that it holds true for the one after that, right? Because we've used the induction hypothesis and we only needed the last two. So we find out that it's true for the next one. Okay, so then I just copy and paste this, but I've got to change it a little bit, right? By the principle of strong mathematical induction, and I'll just add an S to this. It holds true for all positive integers. Okay. That's all, guys. Do you have any questions about that? Are you all still here? Okay, anyway.